Hello, everybody. Welcome back to Calc 3. Plan for today is we are going to push forward in Standard 3. We're going to get most of the way through the rest of Standard 3 today. And then on Friday, we'll, in the first 15 minutes or so, finish up Standard 3 and then jump into Standard 4, where we'll be looking at how to find formulas for lines and planes in R3 and up. Office hours, I guess this one's already over. We've got office hour this afternoon from 2 to 3. Tomorrow, I had to cancel my morning office hour, so I'll only be available 1 to 2 tomorrow. But I am going to hold an extra bonus office hour Friday morning in the hour before class from 10 to 10:50. As far as homework goes, I posted some practice problems from Standard 3, which you should mostly be able to work through after today's class. And the Standard 3 quiz is going to be on Monday. We won't quite finish Standard 3 today. We'll get close. So then Monday will be the quiz day for Standard 3. Anybody have any questions or comments before we get started for today? What is the best cure for a bad case of the right angles? The best cure for a bad case of the right angles is the Pythagorean theorem. Okay, so let's see. In Monday's class, we introduced this new algebraic operation called cross products that only worked for two vectors in R3 specifically, where if A and B are vectors in R3, then their cross product is going to be another vector in R3, and we kind of came up with a geometric definition of what the cross product does, and that the length of the cross product should be equal to length of A times length of B times sine of theta, where theta is the angle in between A and B, which should be equal to the area of the parallelogram spanned by A and B. Meaning, if this is your vector A, and say this is your vector B, then we can kind of complete this drawing to make a parallelogram. The area of this parallelogram should be equal to the length or magnitude of the cross product. And the direction that A cross B should point in, A cross B should be orthogonal to both A and B, meaning perpendicular to both of the original two vectors. And it needs to do it in a way such that this set of vectors, A, B, and A cross B, satisfies the right-hand rule. Meaning, you stick out your right hand, you point your fingers in the direction of A in a way so that they can sweep inwards towards B. Your thumb should be pointing in the direction of A cross B. And we kind of talked about a bunch of properties of the cross product yesterday based on this geometric definition. Kind of gave us a lot of nice intuition about how the cross product works. That, for instance, if A and B are both parallel or anti-parallel, then the cross product is just the zero vector. We said that this only works in R3 because of the direction component. If we're in R1 or R2, we can't necessarily find a direction that's orthogonal to both of the original two vectors. And if we're in R4 and higher, then there's too many directions that the cross product can point in. And the only issue with what we did in Monday's class was it didn't give us a nice way to actually compute these cross products. So I just give you two vectors in R3 and say, tell me what the cross product is. This is not a nice way to try and compute it. You could sort of compute length if you feel like doing sine of inverse cosine of the dot product divided by the product of the magnitudes, but that doesn't sound fun. And this direction, forget it. Try to get an accurate answer by seeing which direction is your thumb pointing in. So what we're going to be focusing on today is sort of an algebraic coming up with an algebraic formula for how you would actually compute these cross products. But before we get into our algebraic formula, we're first going to need to talk about matrices, which are going to kind of be a key component for the rest of the semester. So if you're following along, I'm on the page in the packet that starts off with, we define a matrix A to be blah, blah, blah. So a matrix is basically, if you've likely seen them before in some math class or another. If you've taken linear algebra, then you're probably sick to death of working with matrices. But a matrix, A, is just going to be in a rectangular array of scalar values. Meaning, it's just going to be made up of like a big rectangle like this, where we're kind of keeping track of a lot of different scalar values. Little a1, 1, little a1, 2, all the way up to little a1n, a2, 1, a2, 2, up to a2n, going all the way down to a sub m1, a sub m2, all the way down to a sub mn. Just sort of like a big rectangle-like thing where we just put a bunch of different scalar values. And it's made up of rows and columns, where when we say something like a21, for instance, that's going to refer to the element in A, and the second row, and the first column. So using this sort of notation, little a sub 2, 1 means you go to the entry in your matrix that's in the second row in the first column. And for a matrix like this that has m rows and n columns, we're going to call an m by n matrix specifically. A is an m by n matrix if A has m rows and n columns to it. So let's look at an example where we actually look at some numbers and such plugged in. Let's say we look at a matrix B that looks something like this. 1, negative 2, 5, 0, negative 8. If an m by n matrix is a matrix that has m rows in it and n columns in it, given this matrix B, what would we say B is a blank by blank matrix? How would we fill in those blanks? Yeah, 3 by 2 matrix. It has 3 rows and 2 columns. So B here, we're just going to say is going to be a 3 by 2 matrix. Where, by the way, if you multiply 3 and 2, or in this case m and n, that's going to tell you the overall number of scalar values that are contained within your matrix. So looking at this, what could we say that little b sub 1, 2 is going to be equal to? Negative 2. We go to the 1, 2 means we go to the first row, to the second column, and that's then going to give us negative 2. How about little b sub 3, 2? Be 4. Third row, second column, going to give us a 4. Finally, one last example. How about little b sub 2, 3?
Doesn't exist.
Doesn't exist, why not?
There's no third column.
Yeah, Zooks. Yeah, that's it. This is telling us to go to the second row, third column. There is no third column. So even though we have little b sub 3, 2, we do not have a little b sub 2, 3. Because there is an entry in the third row, second column, which is just 4, but there's no entry in the second row, third column, because there is no third column. In general, the notation we use is, if we are talking about the matrix as a whole, we typically use a capital letter, like this is the matrix big A. This matrix is big B. But usually, if you want to talk about an individual scalar value within that matrix, so like 5 or 4 or -2, we typically use a lowercase version of that letter. So big B is the matrix itself. Little b is going to refer to individual scalar values within the matrix, like little b sub 1, 2, little b sub 3, 2, etc. These matrices, oh boy, they're going to be important to us for the rest of the semester. Kind of one big way in which they're going to be important is that I think it's going to be standard 8 when we first start talking about derivatives of multivariable functions. In Calc 1 and Calc 2, anytime you see a derivative, it's just going to be a number. Like if I were to tell you, hey, I have a function f of x, what's the derivative at x equals 2? You might say, oh, the derivative at 2, that's going to be -3 because the slope of the tangent line is -3. In Calc 1 and Calc 2, derivatives are just individual scalar values. In this class, our derivatives are actually going to be matrices. They're going to be kind of rectangular arrays of values once we start getting into derivatives. But that's several standards for now. Once we start getting into the calculus part of the class, right now we're still kind of working our way through the vector algebra. So Dr. Gerstel, what does this have to do with how to find the formula for a cross product? Well, it's going to turn out that how we can actually compute cross products is going to rely on the use of these matrices. And in particular, it's going to rely on how to take a determinant of a matrix. So let's write that out. If you recall, we had back in Standard 2, we had a way of going from vectors to scalars using dot products. You take the dot product of two vectors, you get a scalar vector. The determinant is going to be another algebraic operation that we can do to a matrix, that takes in a matrix and is going to spit out a scalar value. So, write this out. Determinants. We define the determinant of matrices in the following way. So for today, all that we're going to need is how to find the determinant of a 2x2 matrix or a 3x3 matrix, meaning a matrix with 2 rows, 2 columns, or 3 rows, 3 columns. When we get to Standard 5, we'll talk about how to find determinants of other dimensions of matrices. But today we're just going to focus on 2x2 and 3x3, because that's going to be what we need for cross products. So if we have a 2x2 matrix, so let's say if we have a matrix A, I'm just going to call the components this little a, little b, little c, little d. The determinant of A is going to be the following. So if you want to find the determinant of A, you can denote that by putting little vertical bars around your A, it looks almost like you're trying to take the absolute value of something. And you can also write that out, the determinant of A, by replacing these sort of big square brackets with just vertical bars around your entries. And that's just going to be equal to A times D minus B times C. That's how you take a determinant. So in other words, you're just going to go kind of down this diagonal and multiply these two, and then subtract what you would get if you were to go down this other diagonal. Sorry, my mask getting caught in my mouth. this other diagonal of the matrix. So, for instance, we could say that if we have a matrix, I'll call it C, that's equal to 1, 2, 3, 4, then the determinant of C, which is the determinant of the matrix 1, 2, 3, 4, according to this formula, should give us what scalar value? If we were to sort of take this AD minus BC formula and apply it to this 2 by 2 matrix 1, 2, 3, 4. I think it's going to be -2. I agree. Because if we take AD, so in this case 1 times 4, subtract what you get going down the other diagonal, 2 times 3, that's going to give us 4 minus 6, or another, which comes out to -2. We've taken in a 2 by 2 matrix, and the determinant will just spit out a single scalar value, -2. So 2 by 2 determinant, pretty straightforward to compute the determinant of. You just do the old, as I like to call it, and my 112 students will might remember this, the old swoosh swoosh. AD minus BC. 3 by 3 determinant is going to be a little bit more complicated, and is going to rely on us knowing how to find the determinant of a 2 by 2 matrix. So for a 3 by 3 matrix, it's a little bit more complicated. We can say that if A is, let's say, A, B, C, D, E, F, G, H, I, the determinant of A is going to be a little bit more complicated. We still use the same sort of notation, A with vertical bars around it, which is the same as just writing it out like this. It's the matrix, but with vertical bars instead of square brackets. First thing we're going to do is we're going to take A, little a, the top left entry, times the determinant of the 2 by 2 matrix we would get if we got rid of the row with A in it, so get rid of the top row, and if we got rid of the column with A in it. So if we got rid of the left column and the top row, we'd be left with just a 2 by 2 matrix, and we need to take the determinant of that, which will be the determinant of EF HI. And we're going to subtract from that the determinant of the 2 by 2 matrix. We're going to subtract B times the determinant of the 2 by 2 matrix we would get if we took away the row and column with B in it. So if we took away the top row and if we took away the middle column, what we'd be left with is going to be D, F, G, and I. And finally, we'll have one more 2 by 2 determinant to find. It's going to be C, the last entry in the top row, times the determinant of the 2 by 2 matrix we would get if we took away the C row and the C column. So in other words, little b, little e, little g, little h. And so that's what we end up with. We basically work our way around the top row, saying entry in top row times determinant of 2 by 2 matrix we would get if we remove the row and column of that entry. With needing to remember to subtract off the b here. And we'll talk about why we need to subtract the b off in standard 5. Which, if we evaluate this out, we'll get A times EI minus FH minus B times DI minus FG plus C times DH minus EG, or if you multiply it all out, AEI minus AFH minus BDI plus BFG, because this minus and distributes, so minus minus becomes a plus, plus CDH minus CEG. EIEIO. So, this one's a bit more complicated than the 2x2 formula. I highly recommend that if you're trying to remember how to take the determinant of a 3x3 matrix, I highly recommend you don't try and memorize this formula because it's kind of a mess. But I don't remember this, just writing it all out in a single line like this. Instead, I think it's most helpful for me, at least, to remember this: that we're just working our way along the top row, adding A times determinant 2x2 of what's left when we remove the A row and column, minus B times determinant of what's left if we remove the B row and column, plus C times determinant of what's left if we remove the C row and column. That's what I find helpful to remember and not try to memorize this gobbledygook. That's a fun word, by the way, gobbledygook. Anybody have any questions about how to find the determinant of a 2x2 or 3x3 matrix? In that case, I want you all to practice an example for yourself. I would like for you all to find the determinant of the 3x3 matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Go ahead and take a minute or two. If you feel comfortable doing so, you're welcome to work with your neighbors or to flag me down and ask for help. I want you to see if you can take the determinant of this 3x3 matrix, and if you do it correctly, you should get an interesting answer. If you feel like you've gotten an answer, I encourage you to maybe check yourself and see if your neighbors agree with what you found. Okay, so is anybody brave enough to share the number that they came up with in the end? Okay.
0.
Got 0? Anyone else? Everybody got 0, or no one else is brave enough? Second one, got it. So let's take a look and see. So if we work our way across the top row, we'll get 1 times the determinant of the 2 by 2 matrix we get if we remove the 1 row and 1 column, 5, 6, 8, 9, minus 2 times the determinant of what we get if we remove the 2 row and the 2 column, which is 4, 6, 7, 9, plus 3 times the determinant of what's left if we remove top row, 3rd column, 4, 5, 7, 8, which we start evaluating. It's going to give us 1 times 5 times 9 is 45, minus 6 times 8 is 48, minus 2 times 4 times 9 is 36, minus 7 times 6 is 42, plus 3 times the expression 4 times 8 minus 5 times 7, so 32 minus 35, which we evaluate out. 45 minus 48 is negative 3, minus 2 times negative 6, plus 3 times negative 3, which, if we simplify, comes out to negative 3 plus 12 minus 9. Negative 3 plus 12 is 9, minus 9. Egads is in fact 0. If there's anyone in the audience who's taken linear algebra, I know there's a few of you who have, is there any special significance to a matrix whose determinant is 0? Turns out, if you know the determinant of your matrix is 0, that's going to tell you a lot of cool stuff in linear algebra about the matrix, such that, for instance, your matrix isn't invertible, it doesn't have an inverse, and that the rows and columns are linearly dependent, and eventually, if you take linear algebra, you get like a 20-part theorem that says, if you know that the determinant of your matrix is 0, here's like 20 things that you can say about your matrix. But we're not going to look at most of those in this class. Not until we get to the second derivative test of this. So that's how we take determinants of 2 by 2 and 3 by 3 matrices. Dr. Gerstl, that is fine and all, but why are we doing this when you told us we were going to compute cross products? So it's going to turn out you can compute the cross product of 2 vectors by setting up and evaluating the determinant of a specific 3 by 3 matrix. So the next thing I want to do is to look at how do we actually do that? How do we find a cross product that uses a matrix? So if you go to the next page in the packet, I give you a couple of determinants to practice finding. I'm not going to go through those in class. Those are just kind of there for you to get a little bit of extra practice if you like to see determinants. I'll be posting my solutions to the packet here in a day or two, and you'll be able to check yourself against me then. So I'm going to flip to the page that starts with what A equals A1, A2, A3, and B1, blah, blah, blah. Here's how we find the cross product. We can say that if vector A equals A1, A2, A3, and B is equal to B1, B2, B3, then the cross product of A and B is going to have a formula of A cross B is the determinant of the 3 by 3 matrix that we get when the second row of your matrix is just the vector A, so A1, A2, A3. The third row of your matrix is going to be the vector B, so B1, B2, B3. And then the first row of the matrix And here's where we get a little bit diabolical. Going to be the standard basis vectors I, j, and k. Dr. Gerstle, you told us that when we define a matrix, all of the entries have to be scalar values. How come your top row has vectors in it? So I did tell you that a matrix has to be made up of scalar values. I lied a little bit. That is the case 99% of the time. But we're going to bend the rules just this once to allow for having a few vectors in just one of the rows. Because when we do that, it's actually going to help us find a nice formula just using the determinant of this matrix here. Because if we evaluate this, we're going to get vector I times the determinant of the 2 by 2 matrix A2, A3, B2, B3, minus vector J times the determinant of A1, A3, B1, B3, plus standard basis vector K times the determinant of A1, A2, B1, B2. Using the same method we did before, you just work your way along the top row, and each 2 by 2 determinant for I, for instance, is remove the row and column with I in it. For J, it's remove the row and column with J in it. Ditto for K. If we evaluate this out, it's going to be standard basis vector I times A2, B3 minus A3, B2 minus vector J times A1, B3 minus A3, B1 plus vector K times A1, B2 minus A2, B1. And this is something that we should be able to simplify and write into just a single vector, keeping in mind that the vector I is 1, 0, 0, vector J is 0, 1, 0, and the vector K is 0, 0, 1. Because what this is going to come out to is a vector whose first coordinate is A2, B3 minus A3, B2. Because when you multiply these two, do these vector scalar multiplications, they're going to have a first coordinate of 0. It's only this first vector that matters in terms of affecting the first coordinate of the sum. Anybody tell me what the second coordinate is going to be of this sum when we combine all of our vectors? Yeah, exactly. It's going to be negative A1, B3 plus A3, B1, or if you prefer, just A3, B1 minus A1, B3. Good job catching a negative sign. My 8 o'clock class screwed that up. We forgot that there's a negative sign out in front of the J, so we have to take the negative of this expression. And then finally, last component, it's just going to be A1, B2 minus A2, B1. And that is how you can compute the cross product of vector A and vector B algebraically. Just like with the formula for a 3 by 3, a general 3 by 3 determinant, I don't like memorizing this as a formula for how to take a cross product because it's just a bit cumbersome. It's just a lot of different terms. It's easy to mix up a minus sign somewhere along the way. So what I usually use to remember is this. Fairly straightforward. Your top row is your standard basis vectors, I, J, and K. Your second row is just your first vector A that you're taking the cross product of. And the last row is just the vector B that you're taking the cross product of. I tend to use this when I'm computing cross products because I find this a lot easier to remember. But if you want to just go straight for using this and you can keep track of that, then by all means, go for it. Up to you how you want to remember this. So let's do an example together where we actually go through and compute the cross product using this determinant approach. And in particular, what I would like to do, I want to compute the cross product of 152 and negative 240. Negative 2, 4. So, in order to compute this, again, we theoretically could use this geometric information about it and say, oh, well, the length of this vector is going to be magnitude of 152 times magnitude of negative 240 times sine of the angle between them. Good luck trying to find the sine of the angle between them without a computer. And the direction is, yeah, we could graph it out and see where the right-hand rule is satisfied. I don't wanna. Use the determinant method. It's a bit more algebraically messy, but it gets us much more accurate results. So, 3x3 determinant. So first row is ijk. Second row is the first vector in our cross product, 152. Last row is the second vector in our cross product, negative 2, 4, 0. We evaluate, it's going to be standard basis vector I times the determinant of what 2x2 matrix? Which determinant are we going to need to multiply by the standard basis vector I? 5240. What we get if we remove top row, left column, minus vector j times which 2x2 determinant? 1, 2, negative 2, 0. Remove top row, second column. Finally, we're going to add to that vector k times the which last 2x2 determinant are we going to need to find? Right? 1, 5, negative 2, 4. D, which is going to give us I times what? 0 minus 8 minus vector j times 0 minus a negative 4, which becomes 0 plus 4, plus k times 1 times 4 is 4 minus negative 10, so 4 plus 10, which gives us negative 8i minus 4j plus 14k, and here is our cross product. It's negative 8, negative 4, positive 14. Boom. No need to mess around with trying to play with your thumbs, unless you want to. It's fun to point with thumbs. We are humans. We have opposable thumbs. This is cool. We don't need to play around with trying to find angles and do trigonometry to find how long our vector should be. This gives us an algebraic approach with the determinant to find, boom, here's our cross product. Is there any quick way that we can sort of check our answer to see if we got it correctly? There's a bunch of nice properties that negative 8, negative 4, 14 should have in common with the original two vectors. You kind of look at our list here. And while some of them are hard to check, there's one thing on this list that the cross product should satisfy that's not so bad to check in comparison with A and B. So what kind of tests can we do in order to check? Did we compute our cross product correctly, corresponding to one of these properties? Area of the parallelogram. Cool. You know how to find the area of the parallelogram fairly straightforward? certainly find the magnitude of this vector. It can be square root of a nasty number. I'll just let you know. I think the issue with that is if we compute the area, if we compute the magnitude of this, we don't really have a nice way to kind of check, is that number what it should be? Because without knowing what sine of theta is, and sine of theta is kind of hard to find, we don't really have anything that we can sort of check the magnitude of this against.
Oh. Okay, so does it have to be orthogonal? Like the dot product has to be 0?
With the original vectors?
Yes.
I think that one's going to be a lot easier to check, yeah. Yeah, that's a good approach. It's hard to check does it have the right length, since we don't know what this expression really should come out to without doing a bunch of trig. Checking this is kind of hard to do. Does it satisfy the right-hand rule? Because I don't really feel like trying to graph these two vectors and then trying to accurately see, does my thumb stick in exactly this direction? But it's one thing that we can check fairly easily is our cross product, is the thing we got for the cross product orthogonal to our original two vectors? Because if we want to check if this vector is orthogonal or perpendicular to the original two, what needs to happen in order, how can we check if this is orthogonal to the original two? We just have to check, does the dot product come out to 0 when we do the dot product? So let's check that out. So here we're just kind of checking. Is -8, -4, 14 orthogonal to the original vectors? And if the answer is yes, then that's a sign that we probably did the cross product correctly. I say probably because it is theoretically possible that it's orthogonal but just doesn't have the right length. But if we do the procedure and we come out with something that is orthogonal to the original two vectors, that's usually a good sign that we probably did it right. So if we compare it, first of all, to, let's say, 1, 5, 2, we're going to get -8 times 1 plus -4 times 5 plus 14 times 2, which will be -8, -4 times 5 is -20, 14 times 2 is 28, and -8 minus 20 is -28, plus 28 is 0. Cool. So our answer is orthogonal to 1, 5, 2, at the very least. And if we check our other vector, which was -2, 4, 0, we're going to get -8 times -2 plus -4 times 4 plus 14 times 0, which is going to be -8 times -2 is a positive 16. -4 times 4 is a minus 16. And then who cares times 0 is 0. And hey, our dot product is 0 still. So the answer turns out to be yes, the vector we found was in fact orthogonal to both of the original two vectors, which means it's probably correct as the cross product. We don't know for sure because it could be correct direction but wrong length, or it could be correct length but it's pointing in the opposite direction, because the negative of this would still be orthogonal to 1, 5, 2 and -2, 4, 0. But this is a sign that we probably didn't make any algebra mistakes along the way. So this does come out to -8, -4, 14. Anybody have any questions or comments about what we did here, or how we went through and actually sort of checked our approach? Is that a hand?
No, sorry.
Oh, okay, just testing out the right hand rule. Got it. Question. So here's a question I have. If we take the cross product of 152 and negative 2, 4, 0, we got negative 8, negative 4, 14. What would we get if we took the cross product of negative 2, 4, 0 and 152? We just took a switcheroo on the order of our vectors. I think we should be able to find this without having to do any additional work. What does that come out to?
Should just be 8, 4, negative 14.
Bingo. The negative of what we got before. The negative of 152 cross negative 2, 4, 0. Because as we said last class, the cross product is anti-commutative, meaning A cross B is always going to be the negative of B cross A, and vice versa. So that is one way that you could be making a mistake that this checking method wouldn't catch. Because if you accidentally try to take the cross product and you put the vectors in the wrong order, you would get the negative of the correct answer, and the negative of the correct answer is still going to be orthogonal to your original two vectors, which is a result of using the dot product properties from standard 2. So that's one way that you have to be careful, is that in general, it's always going to be the case that if we were to set up the dot product of A and B, which would look like this, versus the dot product of B and A, which is the same matrix but with the last two rows swapped, so this will be B cross A, this will be A cross B. These are not going to be equal to each other. They're negatives of each other. So that is something that's important to do when if you're setting up your determinant. Make sure your second row in the matrix is your first vector in the cross product, and the last row in the matrix is the second vector in the cross product. Because if you mistakenly swap the order of these two rows, you're going to get the negative of what the cross product should actually be.
So is it the negative of the determinant for A and B? Like we don't take the determinant of the second matrix and then minus it, right?
Yeah, if you wanted to get the same thing as A cross B. If you were to, basically here what I'm saying is if you swap the last two rows in the determinant here, the result you're going to get is the negative of what you started with. So this expression, if you remove the minus signs, you just get a matrix for B cross A and B cross A. But if you want to compare that to A cross B and the determinant matrix for that, you have to have a negative sign that shows up here. Because without the negative sign, seeing the determinant of that is equal to the determinant of that would be incorrect. Good question?
Is there any time that we would use B cross A instead of A cross B?
Not really. There are a lot of times when it doesn't matter, where either one would suit your purposes. For instance, in standard 4, the next standard, when we're looking for formulas for planes, we're going to oftentimes be faced with the task of, I have two vectors, A and B, and need something orthogonal to both of them. Doesn't matter what, just needs to be orthogonal to both of them. In that case, you could take A cross B or B cross A, and either one would suit your purpose, even though they technically would give you two different vectors, because either one would be orthogonal to both the original two vectors. But if you wanted to specifically have A cross B in the way that makes the right-hand rule work, which sometimes you want to have happen in, say, physics, looking at quantum physics, I know that shows up, then it does matter. But for a lot of what we're going to be doing in this class, you could use A cross B or B cross A. That being said, if I asked you evaluate this cross product on a quiz or something, then you better do it this way and not the other way.
Yeah.
Alright, good question.
So the top row of the determinant here, the IJK,
Mhm.
that's also a matrix, isn't it? So is that why we get a
Yes.
vector as a determinant instead of a scalar?
Yeah, so the fact that our top row is made up of vectors and not scalar values like it normally is when you do matrices, that's what's going to cause the determinant of each of these matrices to become three-dimensional vectors, when normally if you take the determinant of a 3x3 matrix where everything's a scalar, it would come out to just be a single scalar valued answer. But the fact that we have an IJK and not just three numbers in the top row means we get vector in R3 corresponding to cross product versus just a single one-dimensional number. These are good questions. Glad you're asking. Anyone else before we move on? We got about 15 minutes left. Okay, so one application of the cross product. In standard 4 and onward, the main reason we're going to care about the cross product, kind of related to back to Tim's question, is because it's going to be helpful for us to know that the cross product gives us a way to find some vector that's orthogonal to two other vectors. But there's also kind of a nice application of the cross product that involves using this length formula. And that's going to be, we can use it to help us find the area of a triangle. So let's see how that would work. We're on the page that has triangles underlined at the top. Let's say I have 3 points in R3. So we're going to say P0 is the point 1, 1, 1. P1 is going to be the point 2, negative 1, 7. And P2 is going to be the point 5, 4, 0. And I'm not going to try and accurately graph these on axes because it would get pretty messy. But I will go ahead and just kind of draw a generic, like, here's like a P0, here's a P1, and let's say here's a point P2. What I would like to do is to find a way, using the cross product, to help us find the area of this triangle.
One way I think to do it would be to set up a vector, or set up two vectors. So at least I kind of looked at this a little bit already. It would be you could set up a vector from P0, a displacement vector from P0 to P1, P0 to P2, and then using that, if you took the cross product, the magnitude of the cross product would be the parallelogram. So if you make parallelograms, the area of the parallelogram. If you divide that by 2, that should be the area of the triangle.
That is exactly correct. Wow, you already went right through all the way to the end there. Yeah, so there's actually a nice approach that says the cross product isn't going to tell us the area of this triangle necessarily, but if we look at the vector from P0 to P1, we write that out as a displacement vector. And if we write out a displacement vector from P0 to P2 as vectors, if we take the cross product of P0 P1 and P0 P2, the magnitude of that cross product should give us the area of this parallelogram right here. And then if we take half the area of the parallelogram formed by P0 P1 and P0 P2, then that will give us the area of the triangle that we're looking for. Yeah, that's good thought on that. Yeah, that's exactly what we're going to end up doing. So first of all, we need to find formulas for these two displacement vectors, one from P0 to P1 and one from P0 to P2. Does anybody else remember how to find the displacement vector? Meaning, if we were standing at P0 if we were standing at, say, the point P naught, what would need to be our change in X, change in Y, change in Z that would get us from P naught to the point P1? We talked about how to find these displacement vectors in standard 1, I believe, but that's going to be something we need to find here. Right?
It's going to be P1 minus P0. So the X is going to be 2 minus 1.
Hold on just a second. Let me catch up. Okay, so 2 minus 1.
And then I can't see.
Oh, sorry.
And then we take 1 minus 1. And then 7 minus 1.
Like that? Yeah, I think I agree. Yeah. Our formula for taking a displacement vector from one point P naught to another point P1 is to just take the coordinates for P1 and subtract off the coordinates from P naught. Or here, even though these, I don't have vector symbols over P naught, P1, and P2 because they're just points rather than vectors. Here, if we want to subtract, we need to use sort of vector subtraction. So I'm going to write a little arrow above P naught and P1 here to correspond to the fact that now we're treating them as vectors rather than as points. Which, according to what I said, should give us 1, -2, 6. Meaning, if we're standing at the point P naught at 1, 1, 1, and we'd like to get to P1, we'd like to get to 2, -1, 7, what we would have to do is we'd have to go +1 in the x direction, -2 in the y direction, and +6 in the z direction in order to get from P naught to P1. Yeah, nice job, Max. What could we do similarly that would allow us to find our displacement vector from P naught to P2? Say that again, sorry. P2 minus P naught. Sounds good to me. That second vector, vector for the second point minus vector for the first point. If we do that, we'll get 5 minus 1, 4 minus 1, 0 minus 1, which will be 4, 3, -1. And that's going to be our two vectors that we need. That the first displacement vector is going to be 1, -2, 6. And the second displacement vector that we need is going to be 4, 3, -1. And once we know these, now we can take the cross product of these two displacement vectors, and then the magnitude of that cross product should give us the area of the parallelogram right here. So let's go through and work that out. So if we take our cross product of P naught, P1 of the two displacement vectors, P naught, P2, what we're going to end up with is the cross product of 1, -2, 6, and 4, 3, -1, which I'm going to choose to use the determinant method. If you just want to plug it right into the final formula, you can. It's going to be the determinant of ijk, 1, -2, 6, and 4, 3, -1. By the way, Tim, here would be a scenario where we could have taken the cross product the other way. The vector we would have gotten the other way would have been the negative of the vector we're going to end up getting, but they would still be two vectors of the same length. And all that we really care about is what's going to be the length of this cross product. So here's a scenario where it doesn't matter which one's first. So that's going to give us I times the determinant of -2, 6, 3, -1, minus j times the determinant of 1, 6, 4, -1, plus k times the stutter today. K times the determinant of 1, -2, 4, 3, which when we evaluate is going to give us I times 2 minus 18 minus j times negative 1 minus 24 plus k times 3 minus a negative 8, which is going to give us negative 16, negative 25, so positive 25, positive 11 for the, and this is going to be the cross product of P naught P1 and P naught P2. So what do we need to do next with this vector? We're ultimately hoping to find the area of the triangle here from P naught, P1, and P2. And right now we have a three-dimensional vector. That's what do we do with that? Let's find the magnitude. Because that's going to give us the area of this parallelogram here that's spanned by our two displacement vectors. I think I'm done with this. Is going to be the magnitude of the vector negative 16, 25, 11, which in standard 2 we learned means just taking the square root of the sum of the components squared. So negative 16 squared plus 25 squared plus 11 squared, which I'm pretty sure anyone who can do basic arithmetic can easily do this in their head and come out to square root of 1002. I lied. I couldn't do that in my head. I just remembered it from this morning. And yes, if this is a question on a quiz to find the area of a triangle, it'll be, this point will have smaller numbers. Not something so nasty to work with as these horrible two-digit squarings. Neato burrito. We found a number now that could represent the area of something. Square root of 1002. Is that going to be the area of our triangle? Tim, so you shaking your head?
You gotta divide it by 2. It's only half of the parallelogram.
Yeah, right now we have the area of this full parallelogram. But if we want the area of just the original triangle from P naught to P1 to P2 and back, you have to just divide by 2. So then the area of triangle is going to be 1/2 times the area of parallelogram, which is just going to be 1/2 times square root of 1002. Which, when I plugged into a calculator earlier, is about 15.827. So the area of this triangle from P naught to P1 to P2 is a little under 16 square units. If this was a quiz question, I would just expect you to, or a test question, I would just expect you to leave it like this: 1/2 times square root of 1002. But thought I'd give you a decimal approximation just for the sake of interest. So, as a reminder, given a triangle of 3 points like this, you can find the area by first finding displacement vectors like P naught to P1, P naught to P2. It's important when you're doing this that your two displacement vectors start at the same point. So you could have done from P1 to P naught and P1 to P2, or from P2 to P naught and P2 to P1, but you couldn't do P naught to P1 and P1 to P2. That wouldn't work. So pick two displacement vectors starting at the same point. Take their cross product, which we did here. Take the magnitude of that cross product to find the area of the parallelogram, and then divide by 2 to get the area of the triangle. This is a nice way to find areas of triangles in R3. You can also use this to find areas of triangles in R2. You just have to do the same process but with a slight twist. And we'll do that on Friday. Have a good day, everybody. Don't be shy about emailing me if you'd like to set up a retest or signing up for an office hour appointment via the Doodle link on Blackboard. And otherwise, I will see you all on Friday.